Last time we looked at the equation for the photoelectric effect, and we left it uh, as as this. Yeah, there's the Ke, kinetic energy for your electrons, and that is equal to a an HF, that's incident energy interacting with your electrons, minus a so-called work function. This equation can be compared with a y equal to mx uh, plus b, okay? And we can identify terms, right? B is minus v. This is the so-called y-intercept, okay? So y-intercept, and we're going to plot on the y-axis, okay? Ke goes on the y-axis, and it looks like frequency goes on the x-axis. X-axis. All right, what does this look like? So we've done the algebra. What does the graph look like? Well, here is my Ke, and here is my, let's say this is my frequency. Okay, it's customary to use EVs for kinetic energy, right? In this topic at least. Not in mechanics, okay, but in this topic definitely. And the frequency here in hertz. Okay, so let's look at the so-called y-intercept. So that's going to be my work function, and it's going to be a negative value. So it looks like a negative value. Let's say it's here, negative Ke. That's my work function for a metal. Okay, so given a metal, that's my work function. Now I need to find what's called the x-intercept. Okay, not the y-intercept, the x-intercept. It's the value of y. Sorry, it's the value of x that makes y 0. X-intercept. So if I have Ke is HF minus V, I'm going to set Ke to 0. Set Ke equal to 0. So force that to happen. What's going to happen now is HF is equal to the work function. But if you remember, the work function is also an energy, so we can express that also in terms of an HF. But HF now here being our so-called threshold frequency, right? That's a threshold frequency. Threshold frequency. We can get rid of the F's and find that the so-called x-intercept is the threshold frequency. Okay, so let's go ahead and do that. Maybe let's do it here. So this is my threshold frequency. Okay. Well, it's going to happen. Let's do a graph now. For values of energy, right, that are greater than my work function, I am able to liberate electrons. And these electrons can contribute to a photocurrent. So I must be able to observe a photocurrent because of electrons moving. That means there's kinetic energy to talk about when the energy, right, HF is bigger than my work function. Okay, so I should have something like that. Okay, according to what happens. Let's do this. Okay, according to my y equals mx plus b, I should have a line, right, that is straight. Okay, something like that. Now, for energies below my work function, I don't get a Ke. Okay, because I'm not, if you remember that analogy of a well, I'm not able to liberate, I'm not able to kick those electrons at the bottom of the well near the top and get them over. Okay, so I will draw this now as a dotted line just to show us, just to remind us that's intercepting, okay? That we don't observe any photocurrent right, associated with this line here. Okay. Now, the final thing to note is that, okay, in orange, this is the slope or the gradient of my line. Okay, the slope. So the slope here, slope is h. It's Planck's constant. Planck's constant. Now, maybe there's going to be another metal. Oh, I don't know. Maybe its threshold frequency. Let's do it in another color. Will this work? Right? Its threshold frequency is there, and that means we should be able to also get a photocurrent for energies that's going to be greater than my work function. Now, I have to respect the fact that these two have the same slope because I'm using the same governing equation here. So this slope here is also Planck's constant h. And I will do, right, using a similar argument that we did for the red line, there is a corresponding work function for my pink line. Okay, so two different metals, properties at least, being graphed here. Here's one, and there's the other. Okay, one has a greater work function, that's line 1. That means I need more energy, right, in order to get a photocurrent going. But look at the frequency, look at the threshold frequency. Right? Look at the threshold frequency for my line, for the metal with a larger work function. That F is big. And that means that the wavelength is short. And this also means because E is HF, if this is big, then the energy is large. Now that makes sense because I have to overcome, I need a large amount of energy to overcome that work function. The same way, if I look at my frequency for my pink line, that's not as large, right? So that means frequency is not as high. I don't have that much energy. Well, look, the work function isn't that much. Okay, so I will need less energy to liberate the photoelectrons for my second method, right, the pink line. You might see a graph that looks like this. So these would be my photocurrent, and here might be a potential, right, a voltage. You might be asked for the following. So here is a potential, and this is a photocurrent. Okay, we might just see something like this. Okay, there's a value of V there. Okay, and we can also have something like this. So this pink line now should go exactly along that red line and start taking off exactly at that red bulb. The intercepts here and here are not really important. What's important here is this line represents light of a given frequency, given wavelength. So it's a known frequency of intense light. This here is light of the same frequency, okay, but more intense. Get more intense. This region here can be distracting. The action happens here. The action happens there because the interpretation of this graph, in particular that point there, is the following. The intensity, right, does not affect, right, the KE, right, the energy of the photocurrent. Now, that's because that would be your stopping potential there, right? So the maximum kinetic energy that these photoelectrons get does not really depend, right, on how intense the beam is, or how intense the light shining on your metal is. Okay, you're always going to get current. You're always going to get some current for given potential. If you succeed now in stopping using a potential, right, stopping the beam of electrons, it doesn't really matter how intense, right? How intense the beam that you're using, you're still going to be using the same potential to stop these photoelectrons, okay? To make your photocurrent become zero. And the interpretation here, right, is this. Okay, the intensity does not affect kinetic energy of electrons. Right. Another small detail, I won't say it's small, but it's usually quoted as the last observation, right? The photoelectric effect. Okay, maybe we can summarize that now, right? The last one, right? Not in any order, okay, would be there is no time delay, okay? No time delay in photoelectron emission. Okay, so what this means is the instant that you put in your light, your radiation acting on the metal, then the photoelectrons are immediately, right, immediately emitted. Okay, how about the others? What are the other